Can you see?
Thank you.
Okay,
Now we can see.
that worked. I'm really sorry. It's just like I recently changed my computer,
No problem.
so
Okay,
I forgot to check
let
about it.
me
Yeah.
present you. To conclude the morning session of this conference, it is a pleasure to introduce Professor Michael Fernandez Gaspar, who is currently conducting postural research at the University of Sao Paulo, but is visiting the University of Miami. Professor Michael Fernandez will speak about on Halin's n-degree conjecture and omega strong cardinals. Please, you may begin your presentation, and thank you.
Okay, thank you for inviting me. And also, I'm gonna be speaking English, but if anybody wants to ask questions in Spanish, if it's slow, then I can understand and address the question. I'll just need to reply in English. So this is recent work of myself, of Gabriel Fernandez from Brazil, who's a professor there, and myself. And we were addressing some questions from Halin's degree conjecture that were mostly settled by Geschke, Krukovka, Melher, and Beetz from Hamburg, where I got also my PhD. So I have a lot of work that intertwine with their work. Um, so what is it about? So I separated these into four parts. So this is about infinite graphs, really. So we can look at a graph and we look at the rays of a graph. This is just like a one-way infinite path. And yeah, just like one vertex connected to another, they're forming a sequence of size omega, okay? And this is an endeavor to try to add direction, some notion of direction to non-directed graphs, right? So we add this structure called rays. Moreover, we say that two rays are equivalent if they are infinitely connected by disjoint paths. So you can go in the same direction and change between these two selected rays. We're going to say at the end they're actually equivalent, right? And we look at the degree, and then, yeah, we have this equivalence class, and we can add a topology to it. Some people in Hamburg and in Brazil are doing that, but I'm not focusing on the topological aspect of the space, but it's an interesting approach. So I look at a cardinal characteristic that's related to the end of a graph, and the end being um, one of the equivalent classes, right? So one of the directions of the graph. So we say that the degree of an n is the maximal cardinality of a collection of pairwise disjoint rays. So they are, of course, they are in the same n, so they are connected, but they are connected by paths, but they are disjoint, so they don't have they are not like one really part of the other. So we're actually taking the path to be independent. And then this notion gave rise to this theorem, which is famous among graph theorists, that says that if we have ends of infinite degree, then they contain a subdivision of the hexagonal quarter grid whose rays belong to that end. So that looks like the tiling of the Euclidean plane, and the borders of the tilings, they are the rays, okay? So this work is really about trying to see what happens for other degrees, like to increase resolution inside of these infinite degrees. Okay, here it really means countable degree. And we're gonna look at different cardinals. And the idea is always to ask, like, so we have this sparseness in the graph, can we still find some kind of nice structure inside of it, some kind of pattern? And for this case, Halin's proved that we can find the hexagonal quarter grid inside of the N. And here we're gonna have some generalization of this concept and ask about different infinite degrees. And this is going to be a ray graph. Okay, so we have a set of disjoint paths of equivalent rays, and we say that the graph that has as vertex at this family of rays is a ray graph if we can find a set P of independent paths. So and the independent paths, they need to have their end vertices on rays from this family. And we form an edge between two rays if there are infinitely many disjoints such infinitely many disjoint paths from R to S that lie in P, right? So we're just trying to add a little more sparseness to the graph. And we say, so when we have an end, a ray graph is a connected ray graph on a degree witnessing subset of this end. So now we can formulate that we have a more general definition of what be the analogous of the quarter grid. We can state Halin's conjecture for any cardinal. So it says that for any graph, if we have an end of degree kappa, then it contains a ray graph that witness this degree. And HC, Halin's conjecture, says it always holds for every cardinal. Okay, so one way to visualize it, unfortunately, I didn't have a picture I wanted to draw, but in Geschke's paper, they have these star. So it's a star, so it's just like it has a common core. Coming out of the leaves of the star, we have various rays, and also one at the center, and we fill it with stars. Okay, so that's gonna be what we call a star of rays, right? So that's the kind of structure that we're trying to find in the end of a graph. So Geschke and these other guys, they conjecture that they had proved all the ZFC cases for Halin's conjecture. And I think this is quite surprising what's going on here, because these really are provable statements about the Aleph function. And they prove things that I see first, that whenever, here I said n in naturals, but it's actually n bigger than 2. So for Aleph 2, Aleph 3, Aleph 4, we can actually find this structure, the star of rays, but it always fails for cardinals whose cofinality is a successor of another cardinal of countable cofinality. So for instance, Halin's conjecture fails for Aleph 1, even though it holds for all the other Aleph n's, okay? And also, the following assertions that are consistent about the conjecture, so using GCH, we can show that for every other cardinal that is not excluded by 2, the conjecture is actually holds. But also it's consistent that for cardinals that having cofinality as being one of the Aleph alphas between strictly between omega and omega 1, the failure of the Halin's conjecture is also consistent. And using similar arguments, we can show the same happens for fixed cardinals that we have there above the first fixed point of the Aleph function. So they didn't know exactly how to obtain without CH positive the positive side of the Hallin's conjecture, only using GCH, but it could be that we can actually prove more than that. So that's what we're trying to do. So they pose this question, if we can actually prove in ZFC Hallin's conjecture for cardinals above Aleph omega 1, or even better, starting from a cardinal, we can actually go above and always have a valid validation of Hallin's conjecture for these cardinal. So we introduced this notion of no, this notion is already known, but we use that. So we say that a cardinal is kappa strong, is theta strong, if whenever we have a smaller cardinal and you raise it to the power of theta, this is still smaller than the cardinal. So we say this is theta strong cardinal. So for example, the successor of the continuum is the smallest omega strong cardinal. If you raise to the power of omega, this is still C plus. Okay, so this is, if you erase like less than that, so continuum many to omega, then it's still less than successor continuum. And this is a theorem with Gabriel Fernandez and myself, and we show that we can actually partition the cardinals into intervals in a proper class of intervals with the following property. So if we have a cardinal above the continuum, and we have an ordinal such that this function that we're going to define later is not the fixed point of the Aleph function, because we're going to use some theorem from PCF theory, from Shalah's PCF theory. So we have that if this cardinal lies in between rash gamma and rash of successor of gamma, the ordinal, then the conjecture will hold in the first, let's say, half of the interval, if it doesn't have countable cofinality, but will always fail whenever this cardinal has countable cofinality, or else it's in the second half of the interval. So we partition these Aleph, this rash gamma plus 1 in half. We go to plus omega, and then we actually have that it holds. Otherwise, we have that it falls, depending on the cofinality of your input. We also prove that the status of HC depends only on the cofinality. If we're talking about singular cardinals, they are rash of limit ordinals. This is a specific case. So as we see, we have a lot of cardinals that for which we can actually prove that Hallin's conjecture holds. And also we have that it does hold for all regular cardinals that are fixed points of the function rash. Okay, so here I'm just gonna try to give you an idea on the combinatorics that are involved. There are a lot of concepts, but the arguments are pretty simple. It's mostly like pigeonhole principle. Yeah. So we have an end of a graph with vertices V and edges E, and we have a subset of the vertex that's disjoint from the end. So we're going to call an epsilon U column is a set of the form R with D, where R is a ray that belongs to the N, and D is a collection of independent sets with ending points in R and U. Okay. So about this, what do we know about these combs is that if we have an N and a collection, a kappa-sized collection of disjoint rays inside of this N, we have these two following lemmas: the combs lemma and the greedy lemma. So the countable lemma is a situation where we have a countable set of vertices and an accountable collection of internally disjoint combs um, for this N and these set of vertices. Then we can find a star of rays, okay, whose leaf rays are spines of a comb in C. So the comb was already defined internally disjoint, but the spines are just like the paths that will lie inside of a set. And so the greedy lemma is to handle the situation where we have a countable set of vertices. And then we have the greedy lemma, which will be some kind of pushback lemma that will help us get smaller and smaller cardinalities until we hit the countable situation. Then we can apply Combs' lemma. Okay, so if we have a cardinal of uncountable cardinality, and it's more than omega, then we can find a set of vertices U of G, a kappa-sized collection of internally disjoint combs, such that U has cardinality less than kappa. So, and all spines of C are in this set of rings. So, as I said, the point will be to get smaller and smaller U's until we finally hit something of that uncountable U. Okay. So, yeah, and we can do that because this is well-founded, of course. So a lambda kappa graph is a bipartite graph, okay, is the relation on the two sides of the set of vertices. The first one, A, has cardinality lambda, which is less than kappa. That's the one of B. And here we have some coherence properties, like, so the last one says that they are independent, they are independent sets that are covering the set of vertices. And this one in the middle is just a technical part of the definition for us that will be needed to construct our graph. And these graphs play a special role in trying to obtain this star of rays because we can form these comps using them. So, and how do we do that? So we start with a kappa collection of rays. They're all lying inside of an n epsilon of a graph, and we say this has cardinality more than aleph 1. So what we can do is to take a set of size lambda of vertices and a kappa size collection of internally disjoint combs of G whose spines are in R. Oops, sorry. And then we can, using these columns, we can define the aleph kappa graph. So they will be the set that was previously A will be U, and the set S of the columns is just the collection of the spines of the columns in C, and we form an edge when V and R, if R is the spine of a column, C such that V is the teeth of T. So this is some ideal combinatorics, some wish that we have. And here we have this lemma that will actually support our proof, okay? And let me see how much time I have here. Okay, so we have lambda kappa bipartite graph, ABE, and kappa is regular, and we have the technical condition here. Then the following happens. If they have countable cofinality, but kappa is omega strong, then there is a lambda analysis 0 kappa subgraph of this graph. And if it has uncountable cofinality, then we can find a lambda prime kappa subgraph of this graph, and lambda is strictly smaller than lambda. So we kind of can use some induction to go back to the previous case, okay? Yeah, of course, kappa needs to be also omega strong in the second case. So, sorry again. And using these, we can prove that the conjecture holds for omega stronger regular cardinals. So just remember that the successor of the continuum is an example. So we're actually using the continuum, really the value of the continuum, regardless of what it is, to partition all the cardinals. Okay, so we consider some situations, and this is a situation where this is weakly inaccessible. Sorry, there's something here. I think I'm going to skip this proof, but because I want to show you the last one, which is longer. So, and here is another technical lemma that says that the conjecture will hold whenever for omega strong cardinals whose cofinality are between, omega strong singular cardinals whose cofinality is at least omega 2. And if the Halin's conjecture holds for the cofinality. So this is how a relation between this is to tackle the singular case, okay? Because clearly here kappa is singular. So we have singular situations with singulars and situations with regular cardinals. So it's not like there is really an interval. There are like intervals that such that the conjecture is alternating, but also, this happens mod some conditions like the cofinality of the cardinal. So something else might happen in the middle depending on the cofinality of the cardinals. And the way that we can actually tackle intervals of cardinals comes from the Chalas PCF theory. So he has this theory that helps us handle cardinal arithmetic, things that can be decided. So for instance, an important consequence is that 2 to the aleph omega is less than or equals than aleph plus 4 or something like that, aleph 4. So those are situations where we can actually say something about the arithmetic of singular cardinals, assuming certain behavior for the predecessors, for the regular predecessors, okay? And this is an important tool to actually prove statements that might hold or might be false for intervals or cardinals. And basically here we have this notion of scale. So just going quickly through that, so we can take a look at some elements. So we have an ideal on omega, countable set of regular cardinals, and we say that two of these functions, they are f is less than g mod j if the set of cardinals for which f is bigger than g is in the ideal, okay? And then we look at the sup of the ideal, and we're gonna say that a family, a kappa size family, in this product is a scale on your ordinal if there is another ideal consisting of bounded subsets. Um, and we have that the functions are in increasing j order, and every other function can be dominated by another one in this family. So this way we have this operator of lambda that, remember, this is the sup of the set A, which is the cardinals for which there exists a kappa scale for lambda. That's it should be like kappa there. So no, not kappa. This is right. This is pp omega lambda. Okay, this is one of the operators. There is also the PCF operators, and Chelas prove various things about this kind of operators. But we're gonna need just the following theorem that says that if we have a omega strong cardinal of countable cofinality, then the pp of lambda is bounded by lambda to the omega. And it's also a consequence of his PCI theory that if it happens that this is not the fixed point, a fixed point of the Aleph function, then this is precisely lambda omega. And this pp is never weakly inaccessible. Okay. I think it's interesting because it's very hard to really tell what the power of a cardinal should be. So using these ideas of PCF theory, we can actually say a lot of things about cardinal arithmetic. Okay. This was like very surprising given the independence phenomena that we cannot decide the continuum, but we can decide some things about cardinal arithmetic. Okay, let me just summarize it. So basically, here is the way that we construct counterexamples for the conjecture. And the first part is really just saying that we can construct. Okay, so what really matters is that we can construct counterexamples out of scales. So here is a very general, the first one is a very general situation where we can have the failure of the Halin's conjecture for regular cardinals. And the second situation is where we can make it fail for also singular cardinals. Okay? So I'm not going through that. I just want to say that the scales are important to build counterexamples. Okay, this is like more the work of Geschke and his co-authors. We just use that and combine this with Shalaz PCF to obtain some results for the intervals, and that can then actually tell. And okay, so this is another situation that we need to tackle, where we can have the failure of Halin's conjecture. So basically, for cardinals, okay, for kappa singular, at least omega 2, if this is the case that And then we have mu less than kappa, and the cofinality of kappa is less than the one of mu. If we can build an increasing sequence of regular cardinals greater than mu, index, let's say here, that's cofinal in kappa such that we can also associate a graph having exactly one end in every degree, and this degree is mu alpha, and it has no ray graph of cardinally above it, then we can also get a failure. So it's also very technical. Maybe I shouldn't have read it, but these two are the theorems that we need to get also to get the failure of the conjecture. So this last one is the failure for certain situations regarding singular cardinals. And here we are ready to prove the main theorem, and how this function rash is defined. Okay, so basically, we start with 2. Our next cardinal is the continuum, and then we're going to do as follows. The continuum doesn't have countable cofinality, so we can raise it to the power of omega. Sorry, we need to add omega successors. So we look at C plus 2, C plus 3, and so on, C plus omega, and then we'll raise to the power of omega, and so on. So for successors of uncountable cofinality, we sum omega many. We look at omega many successors and raise to the power of omega. And when they have countable cofinality, we just raise to the power of omega. And at limit steps, we take unions. Okay? So that's the function. And yeah. Okay, so we have some situations here that let me just go back to the statement of the main theorem here. Okay, so we have the first half of the interval. These will hold in certain situations, and it will fail in the second half of the interval. So let's see. Okay, so considering in the first half of the interval, we can just do some induction for the cardinals and prove that for the cardinals that are lying there, they are omega strong. And then we have lemmas that say that the conjecture holds for omega strong cardinals. So that was easy. Now for case B, we have our subcases. So we need to assume that it doesn't have countable cofinality, and now it's in the second part of the interval. Then using Chalais' PCF theorem, we can compute the PP of these plus omega, and that will give us exactly the rash of the successor, so the end of the interval. Okay, so, and by the definition of the PP operator, this will mean that we can find the scale for this ordinal, and it will follow that the conjecture fails because the existence of the scale. So for the second subcase, there's a typo here. We look at the end of the interval, and we say that if there is a scale for this n for hash gamma plus omega, then it also follows that it fails. Okay, this is the situation. Or we can since it follows from the theorem that this is not weakly inaccessible, since this is the suit of this is the PP, so it is a singular cardinal. Then we can apply the failure for singulars to get the failure for Halin's conjecture. And the other situation is when we have countable cofinality. So it's going to fail for everybody of countable cofinality throughout the interval. And we need to use that this is not a fixed point of the Aleph function, and apply also again the theorem. Then we can use the counterexample from scales. So it follows really directly that it fails from the last PCF. In the last subcase, we can again consider the situation where we have a kappa scale for hash gamma. Then again, this is going to fail just because counterexample from scales. And otherwise, we just use the failure for singulars. So basically, all those lemmas that we prove plus PCF theorem, they will tell us really what are the points where the conjecture is failing or holding, right? Okay, so there is also case 2, which is a little technical, like whether it depends on the cofinality. And the last case only follows from the fact that the cardinal is regular and omega strong. We already have proved this lemma. So that was it. Here, some comments about independence, but I think I'm gonna finish here. So there are basically here, there are some situations where we cannot say some things, and those depend on the singular cardinal hypothesis, and that's related to large cardinals. So for instance, if this hypothesis, the singular cardinal hypothesis holds, then the conjecture holds for successors cardinals that are above the point where the hypothesis hold, as long as they don't have a certain form. But also, we can say that the conjecture fails for successors of cardinals of uncountable of cofinality different than omega that are above the continuum, whose successor is larger than continuum. And if this happens, I'm sorry, then we can find a model with a measurable cardinal, theta. And basically, yeah, and this has disorder type theta plus plus. So basically, this is saying that certain failures for Halin's conjecture imply the existence of measurable cardinals already, right? So that's all, again, I think. Okay, some more corollaries, but I think that's it. Those are the references, and this is my only word in Spanish. Gracias.
Thank you very much.
Thank
Thank you very
you.
much. It's a very interesting topic. Any question from the public? El profesor comentó que podían preguntar en inglés o en español sin problema. No questions.
So I think there will be a preprint pretty soon coming up on archive. Yeah, with a lot more details, and I need to fix some typos also, but pretty soon there will be something.
Okay. There being no questions, I share with you your certificate as a speaker at this 4th International Congress of Topology and related topics. We hope that you can continue participating in the following years. Thank you very much.
Thank you.